This is a fun lesson. In this video, I'm going to teach you how to count. Now, most of you probably think you already know how to count, and you would be correct. But you know how to count, you were taught how to count back in kindergarten in one particular numbering system, and there are actually multiple numbering systems. So this lesson is about how to count using different numbering systems. So in order to understand how to use other numbering systems, I'm going to start by teaching you what you already know. Okay, and that's important because all of the numbering systems follow one basic rule. And so if we take a moment and talk about the things that you already do automatically, and then you can apply that same rule, that same principle to the other numbering systems, just making the necessary adjustment. Okay, so we're going to start by talking about the numbering system that we all know. And it's referred to as the decimal numbering system. Okay, it's also known as base 10. Okay, and the reason we call the decimal numbering system base 10 is because we have 10 unique digits that we use to count. Okay, and what are they? They are 0 through 9. Okay, I pause there for a moment because most people tend to think that we start counting at 1. That's typically where we begin. But when talking about the numbering systems and really understanding how they work and how we count, we have to start at 0 because that's the first unique digit that we have available to us to count with. Okay, so how do we count in the decimal system, base 10? Okay, we start at 0. Okay, after 0 comes 1, 2, and then all the way up to 9, and that is our last unique digit. So the question I have to ask, and this is the rule that all the numbering systems follow, is what do you do when you run out of numbers? Okay, when you run out of unique digits, what do we do next? Okay, and the answer that you know instinctively is that to the left of this group of numbers, we might call this the ones column. To the left of the ones column, we have what we call the tens column. And in that tens column, initially, we just have zeros, okay? Because there's nothing there, okay? But that helps us answer the question, what do we do next when we get to 9? Okay, so here we are. There's the number 9, okay? We increment the column to the left by 1. So we increment from 0 to 1. And then over here in the ones column where we've been doing our counting, we go back and start over. Okay, so that's the rule right there. That's what you need to know. In every numbering system, you go through all of the available unique digits, and then when you run out, you increment the column to the left and start over. Okay, there you go. I just taught you how to count. Woohoo! Let's move on to the next numbering system. This one, it's kind of a dead numbering system. It doesn't get any use anymore. There used to be a value to it. I like to go here with the next step in the lesson because it helps underline what I just said and it starts to build the theme. Okay, so the next numbering system I want to talk about is octal. And you can probably guess by the name, it's referred to as base what? Octal, probably base 8, which means we have 8 unique digits available to use. Okay, what are they? 0 through 7. There's 8 unique digits. Okay, so when we start counting in octal, we start at 0, and then 1, and then 2, and so on and so forth, until we get to 7. And that is where it ends. Okay, we have no more unique digits available to use when counting in the octal system. And so what do? We increment the column to the left and start over. So not shown here, understood, is that number is 0, 7. Change the 0 to a 1 and start over. Okay, so what we commonly know within the decimal system, the counting system that we learned in kindergarten, the number 8, is represented in the octal system by a 1 and a 0. Okay? So it seems a little weird. but we can see the theory at work, right? We just carry on from here. 1, 1, 1, 2, until we get to 1, 7. We've run out of unique digits. What do? We increment the column to the left. 1 becomes a 2. And we go back and start over. Okay? And so that's the numbering system. That's how that works. All right. That's Octal. Like I say, it doesn't really have a lot of functionality anymore. Okay? Let's move on to something that still does exist. Or does exist, I should say, still has use and value. Octal still exists. It just doesn't have a lot of use. Okay, the next one, you've probably heard this term, maybe not had it explained as to how it functions. Okay. The hexadecimal system. I always hesitate on my spelling. Yeah, that's what I thought. It's actually the hexadecimal system. That's better. Better get it right. And what is its base value? How many unique digits do we have in the hexadecimal system? Base 16. Okay, so this is going to require a little bit of explanation, because what are the rest of the numbers? Okay, 0, 1, 2, on to 9. That's pretty straightforward. But what do we do from here? Okay, we can't go to 10, okay, because that requires 2 digits. We still have to work within just a single digit to get our 16 unique digits. So what comes after 9? The letter A. And then B, C, D, E, and F. Okay, so the unique digits in the hexadecimal system are 0 through F. Okay? And what do we do next? Same rule applies. Increment the column to the left and start over. So, understood is the fact that there's a 0 there. We're going to change that 0 to a 1. And we start over. Okay? Just like that. All right? I'm going to eliminate this. There's how we count in hexadecimal. We get to that point and we just carry on, right? Go through our A, B, C, D, E, and F every time. Okay? So we have 16 unique digits, 0 through F. There's a very good reason for this once we move into the whole point of this conversation, which is understanding how a computer thinks. Okay? We've seen that within an input or an output card, we have 16 slots available. Okay? 0 through 15 is how we refer to them, but it lines up right here with the hexadecimal system with 0 through F. 16 unique digits available to use. So in the computer world, when we try to understand how a computer thinks and keeps track of things, this base 16 has a very real value to it. Okay? And to understand what that value is, we need to move on to the last numbering system that I want to talk about. Okay, there's actually 2 more things we want to talk about. One's a numbering system. The other is more of a translator. Okay? So if we're having this conversation to understand how a computer thinks and how a computer keeps track of things, then we need to talk about the one and only language, the one and only numbering system, the one and only thing that a computer understands. Anybody know what that is? The binary system. Okay, binary system is referred to as base 2. And how many unique digits do we have? 2. What are they? They are 0 and 1. Okay? The only thing a computer understands is a state, a condition. Okay, 0, 1. True or false, yes or no, high or low, hot or cold, up or down, left or right. Okay? That's the only thing that a computer knows. Okay, it knows a lot of them, but it really comes down to just zeros and ones. Okay, so how do we count in binary? We start at 0, we go to 1. Now what do? Start over. Increment to the left and begin again. We just ran out of numbers again. Increment to the left and start over. We just ran out of numbers again, didn't we? Increment to the left and start over. Well, we don't need to build to the left. This can remain as is. This is the one that has to increment to the left and start over. So that's going to turn to a 1, and that's going to turn to a 0. Okay, now 1, 1, 1. Here's where we have to increment and start over. So this has to increment to the left, but this has to increment to the left, but this has to increment to the left. And all of these start over. Increment. Increase by 1. Just in case I'm throwing a word out there that you're not familiar with or comfortable with. Okay, increase by 1, that next column over. So here's counting in the binary system. Okay, it looks really, really awkward and clumsy. Very quickly it becomes uncomfortable. Okay, but there's a simple way that we can figure this out. Okay, so way back in the beginning with the decimal system, I talked about that ones column and then the tens column, and you know that the next is a hundreds column and a thousands column, 10,000 column, so on and so on and so forth. Okay, we want to do the same thing here in the binary system. Okay, so look at what happens. If we have just a 1 in this first column, what does that represent? Well, maybe we should do this. Let's take these numbers and write down what they represent in our familiar decimal system. A 0 is a 0, and a 1 is a 1, and this is a 2, and this is a 3, and a 4, and a 5, and a 6, and a 7, and an 8. Okay, so if we have nothing but a 1 in this first column on the left, what number does that represent? That represents a 1. So we are going to call this the ones column. Okay, that's a 1. Okay, so if there is a 1, if there is a true in this first column on the left, that's going to represent a value of 1. Okay, what if we have a 1 only in the second column from the left? All right, here's this situation here. So the second column is true, everything else is false. That represents the number 2. So this second column represents the value of 2. Okay? What if only the third column is true? Here we are here, the third column is true, everything else is false. That represents the familiar number 4. So this third column represents the number 4. And what if only the fourth column is true? So now we move over, here we've got a bunch of variations, and finally right there, that fourth column is true, everything else is false. That represents the number 8. So there we go. That is how we figure it out. So we look at this column right here, for example, and we have a true value in the column that represents the number 4, and a true value in the column that represents the number 1. Add them up. 4 plus 1 equals 5, and that is what that 101 represents, is the number 5. Okay, so this is how we figure this out. 1, 2, 4, and 8. Okay, we haven't completed it here. I don't have enough room, but let me ask you the question. What if all 4 of these columns were true? If we had a 1 in each of these spots, 1, 1, 1, 1, what does that represent? Well, 8 plus 4 plus 2 plus 1 equals 15. There's that number we've been looking for. So we have within this collection of 4 numbers, within this collection of 4 ones and zeros, we can identify the numbers 0 through 15. Okay, which lines up perfectly with the hexadecimal numbering system. Okay, and that's why hexadecimal has such value when working with computers, because any 4 bits, these all represent a bit within your computer's operating system or memory system, any collection of 4 bits can be used to represent the numbers 0 through 15, or 16 unique digits, as is the case with the hexadecimal numbering system. Okay, so that's why hexadecimal and binary line up perfectly. Okay, that leads us into the final thing that I want to talk about. So the binary system and the hexadecimal system line up perfectly. Okay, we've got that, we call it a 4-bit byte. Okay, 0, 0, 0, 0 equals a 4-bit byte, which, and apparently it was Apple that came up with this terminology, so the pun is entirely intended. A 4-bit byte equals a nibble. Okay, and we can use this nibble, this 4-bit byte, to line up perfectly with the hexadecimal system, 0 through 15. Okay, the problem is that we are not comfortable with the hexadecimal system. We didn't grow up learning the hexadecimal system in kindergarten. We learned how to count using the decimal system. So we need, in order for the computer to be useful for the general population, general public, we need to be able to work within the decimal system. However, the computer only knows ones and zeros. So we have this thing called BCD. Okay, and BCD stands for binary coded decimal. Binary coded decimal, BCD. And what that means is it's coded in binary. We must count using ones and zeros. That's how the computer has to function. Okay? But while counting using ones and zeros, we are going to count using the rules of the decimal system. Okay? And what are the rules of the decimal system? Start at 0, go to 9, and then you increment the column to the left and start over. Okay? So what that means, what BCD is going to do, is it's going to use a nibble to represent the ones column. And then it's going to use another nibble, another 4-bit byte, to represent the tens column. And so on. It can use another nibble to represent the hundreds column, and so on and so forth. Okay, so it's going to start here at 0, and then it's going to go to 0, 0, 0, 1 to represent the number 1. It's going to go to 0, 0, 1, 0 to represent the number 2. It's going to get all the way up to, let me see if I can do this, 1, 0, 0, 1 is going to represent the number 9, right? So there's a 1 in the 8 column to represent 8, plus a 1 in the ones column. So that is the binary number 1. And then what happens next? Well, binary is capable of carrying on, right? But because this is binary coded decimal, we're going to follow the decimal system while counting in binary, which means we're not going to go any further with that nibble. Okay, that's the number 9. Okay, the rules of the decimal system say that once you get to 9, you have to increment the column to the left and start over. And so that's exactly what we're going to do. Up until this point, the tens column has been filled with zeros. But now we're going to increment this column so that we now have a 1 in the ones column. Sorry, we have a 1 in the tens column. The ones column is going to start over. Okay, so binary coded decimal means that we're counting in binary. It is unquestionably nothing but ones and zeros. All right, but we are following the rules of the decimal counting system so that we're not taking this nibble all the way to its maximum, which is 15. We're going to stop at 9, because that's the rule of the decimal system. Okay, so there you go. That is how to count.